What keeps an aircraft safe when every system must work under enormous forces, precision, and zero room for error? From elevators moving jets at sea to transport aircraft, landing gear tests, engine maintenance, runway safety, and final assembly, aviation engineering is a chain where every detail protects the next flight. On the nuclear-powered carrier USS George Washington, aircraft movement is not limited to the flight deck. An aircraft elevator links the hangar bay below with operations above, carrying aircraft, equipment, and personnel between levels. From inside the hangar, the platform rises until the flight deck appears ahead. Once level with the deck, the elevator becomes part of the surface. Sailors control the area, guide people away from the edges, and prepare the platform for the return trip. Looking down, the sea is visible beside the carrier, while the island structure marked with number 73 provides a fixed reference. The platform then descends smoothly into the crowded hangar bay, showing how naval aviation depends on vertical logistics before aircraft can launch. From moving aircraft onboard ships, the challenge now expands to moving industry. In Croatia, a transformer weighing about 140 tons begins its journey at the Končar factory, long before it reaches an aircraft. The road convoy itself is an engineering operation. A 12+12 axle trailer is controlled by 4 push-pull tractors, creating a combination roughly 90 meters long with a total moving weight approaching 400 tons. The transfer is scheduled at night when traffic is limited, and the 3.5-hour route to Zagreb Airport can be managed with fewer interruptions. Waiting at the airport is the Antonov An-225 Maria, built on a scale that makes even this transformer look manageable. The aircraft measures 84 meters in length, spans 88.4 meters across the wings, and has a maximum takeoff weight of 640 tons. Its cargo compartment provides about 300 cubic meters of space, with a usable hold roughly 43.35 meters long, 6.4 meters wide, and 4.4 meters high. But size alone does not solve the loading problem. The transformer must first be secured to a specially designed transport frame, spreading the enormous concentrated load across the cargo floor. Engineers then coordinate lifting, alignment, and pulling as the transformer advances into the nose-loading aircraft inch by inch. Every movement must remain centered and controlled, because small errors at this mass can become major structural problems. Throughout the loading sequence, aviation engineers supervise clearances around the transformer, the frame, and the cargo compartment. The aircraft cannot simply absorb a heavy object anywhere on its floor. Position, load distribution, restraint geometry, and movement all determine whether the payload can be carried safely. Inside the hold, the load is finally restrained using 120 steel cables. Their purpose is to keep the transformer fixed inside the cargo compartment. The operation demonstrates the discipline behind exceptional air transport. Road movement, Load distribution, aircraft positioning, steel restraints, and engineering supervision must be completed as one coordinated process before departure. After loading a giant aircraft, the next challenge is lifting one whole. In Fuenlabrada, a Boeing 707 fuselage arrives by oversized road transport for a carefully planned heavy lift operation. With the aircraft resting on its trailer, crews prepare two large aguado cranes on opposite sides of the load. Their lifting lines are connected through broad sling arrangements designed to support the fuselage without concentrating force at a single point. The lift begins slowly. Both crane operators must raise in coordination so the long airframe remains level while its weight transfers away from the trailer. Workers on the ground hold guide ropes, controlling rotation and limiting unwanted swinging as the fuselage clears the transport equipment. Guide ropes remain under constant control so the fuselage does not swing while suspended, especially as the cranes move it across the fence toward the designated staging area. Once fully airborne, the Boeing 707 is guided across a fence toward its new staging or display area. The cranes continue making small corrections while the ground team watches clearances from several directions. Lighting and support vehicles make the nighttime operation possible, but visibility and communication remain essential. This is aviation engineering outside the airport environment. Instead of generating lift through wings, the aircraft depends entirely on crane geometry, sling placement, synchronized hoisting, and human control. The same airframe designed to move through the sky must now be treated as an oversized suspended structure, where stability matters more than speed, and every meter of movement is deliberate. Only after the fuselage is stable over its destination can the crew lower it carefully and release the lifting system safely. From lifting an airframe externally, we move inside the machinery that powers it. At Miami International Airport, technicians replace the fan blades of a GE90 engine fitted to a Boeing 777. The work begins at the front, where technicians use specialized tools to remove the spinner cone covering the center of the fan assembly. With the spinner removed, the used fan blades are taken out one by one from the fan disc and transferred to storage racks. Replacement composite blades are then brought forward and carefully slid into their individual slots. Each replacement blade is seated in its assigned groove, while technicians continue checking spacing, alignment, and the blade root installation against required flight safety standards. Technicians inspect the blade roots, spacing, alignment, and retention points before completing the assembly. Once every replacement blade has been installed and checked, the spinner cone is realigned and secured in its original position. The finished engine may look unchanged outside, but its largest rotating stage has been rebuilt through controlled, repetitive precision for safe flight. Engine reliability is only one link. Landing safely depends on another moving system. In a hangar, a Boeing 777 is raised for a landing gear retraction and extension test. Hydraulic power opens the gear doors, allowing the main landing gear and nose gear to begin folding toward their bays. Each main assembly, carrying 6 wheels, rotates through its path before disappearing inside the aircraft. The sequence is then reversed. Doors open, the gear extends, and the assemblies move into the down and locked position required for landing. Technicians repeat the cycle, watching hydraulic pressure, motion, sensors, and locking indications. Repetition confirms that the system can perform reliably before the aircraft returns to service. The same principle appears on the A320, but through a simpler 2-wheel assembly. The main gear extends, straightens, and mechanically locks securely for final inspection. From landing mechanisms, engineering now shifts to mission equipment fitted inside airframes. At Osan Air Base in the Republic of Korea, technicians from the 25th Fighter Generation Squadron prepare an A-10 Thunderbolt II for installation of its GAU-8/A Avenger cannon. The aircraft is positioned inside a hangar, where the crew organizes tools and inspects the gun bay, surrounding connections, and working area beneath the nose. The 7-barrel 30mm cannon assembly is carried on a dedicated BL-23 handling vehicle. Instead of lifting the component by hand, technicians use the support equipment to control its height, angle, and movement as it approaches the opening under the aircraft. The assembly is advanced gradually until it aligns with the mounting position inside the fuselage. A hydraulic lifting system then raises the gun into the bay. Technicians use lights to inspect mechanical interfaces, verify alignment, and check locking points as the assembly seats into position. Connections associated with the ammunition feed system are also checked before the installation can be considered complete. The process shows how aircraft maintenance often depends on precise ground equipment as much as the aircraft itself. A large component can only become part of the airframe when its support points, interfaces, and connections match exactly. Once secured and inspected, the A-10 can move toward its next readiness checks. Careful alignment prevents force from damaging surrounding aircraft structure. After a complex component installation, safety engineering turns toward emergency escape systems. On a Boeing 747 freighter, the upper deck exit opens, releasing the packed slide. High-pressure gas automatically inflates and extends it toward the ground below until the evacuation path becomes fully usable. Emergency systems protect people, while ground systems keep aircraft moving between flights. The Liquip 1000 series beta-wide body cart is designed to refuel aircraft from an airport hydrant network. Ground staff tow the unit into position and connect its supply hose to the underground hydrant pit. A scissors lift platform raises the technician to the wing refueling point, where Jet A hoses are connected directly to the aircraft. During transfer, ElectroCount LCR2 meter displays and monitors the flow of fuel. The system combines access, pumping connections, and measurement in one mobile platform, helping crews complete refueling accurately while reducing ground turnaround time. Behind airport operations lies a wider world of material handling technology built for precision. Terex Material Handling and Port Solutions brings together lifting equipment, industrial drives, harbor machinery, and integrated control systems used across heavy industry. Under the DMAG name, the portfolio includes cranes, hoists, and drive systems that can support applications ranging from manufacturing and recycling to renewable energy and aviation. One long-running example is the DMAG KBK light crane system, introduced in the 1960s. Its modular structure allows layouts to be customized and expanded as production requirements change, a principle that remains important in factories where components must be moved safely through confined work areas. The Port Solutions side addresses a different scale. Systems are designed for loading, unloading, transporting, and storing bulk materials in containers, with operations ranging from manual control to semi-automated and fully automated handling. More than 850 mobile harbor cranes are described as operating across 300 ports worldwide. The broader engineering lesson is integration. Cranes, container transport equipment, stacking systems, and management software are most effective when they function as one coordinated network. Aviation factories and airports depend on the same idea. Moving a complex machine safely requires not only the aircraft, but an entire ecosystem of handling equipment around it. Precision matters when every supporting machine works together. That supporting ecosystem extends beyond airports to naval aviation over open water. During Marine Festa in Hachinohe in 2013, the Japan Maritime Self-Defense Force demonstrates how ships and aircraft operate together in a coordinated maritime environment. Guided missile destroyers, including JS Atago and JS Ashigara, lead formations across the sea, establishing the moving surface picture below. A smaller missile craft, Kumataka, accelerates across the water and deploys infrared decoys, creating a large smoke-filled defensive screen. Above the formation, a Lockheed P-3C Orion patrol aircraft descends to lower altitude and releases bright flares designed to counter infrared-guided threats. The demonstration then shifts to the Shinmaiwa US-2 rescue amphibian, flying extremely low over the sea. The aircraft passes near spectators aboard JS Shimokita, showing the controlled low-altitude capability required for maritime rescue operations. Here, aviation engineering is inseparable from the operating environment. Sensors, defensive systems, low-level flight control, and coordination with ships all shape how aircraft are used safely and effectively over water. At sea, accuracy must remain dependable, despite constant platform movement. From coordinated flight at sea, we return to heavy airlift across mountains. On the night of May 19th, large drop-box units are moved to Arturo Merino Airport in Santiago, Chile, beginning a transport chain that combines aircraft, trucks, and cranes. The cargo is loaded into an Antonov An-124, a heavy transport aircraft with a stated payload capacity of 150 tons and a crew and technical team of 19. The An-124 carries the units across the Andes from Santiago to Mendoza, Argentina. After the flight, the logistics operation continues by road, with trucks transporting the drop boxes from San Juan toward the Veladero mine. On May 22nd, cranes lower the equipment into its final fixed position. The units are designed to control flow speed and pressure in process lines while also providing shut-off valves for individual pipelines. Once aircraft return from demanding missions, maintenance also includes cleaning efficiently. At Taiwan Taoyuan International Airport, EcoShine offers an alternative to traditional washing. A Boeing 777-300ER can require about 10 tons of water under conventional methods. EcoShine, transferred from France, uses only around 1 to 2% of that amount. Its nano-based cleaning solution produces almost no wastewater and is described as non-toxic, non-volatile, and non-flammable, improving efficiency and safety. Clean, inspected aircraft must finally prove that every system works under power. During an exercise, an F-22 Raptor begins with startup procedures as the auxiliary and main propulsion systems come alive, producing the characteristic exhaust and sound of the aircraft. The pilot boards the cockpit while ground technicians complete checks around the fighter. Once cleared, the F-22 joins other aircraft and taxis in formation toward the runway under ground guidance. This slow movement is the final transition from maintenance environment to flight operations. At the runway, engine thrust rises, the aircraft accelerates, and the Raptor lifts away before climbing and maneuvering overhead. The sequence connects engineering to its purpose. Every inspection, service action, and ground check ultimately supports controlled flight. That transition from runway to flight becomes even more demanding in close formation. The United States Air Force Thunderbirds demonstrate this with F-16 Fighting Falcons flown in tightly coordinated groups. After ground preparation and taxi, the aircraft move into the familiar diamond formation, placing several jets close together as they begin the display. The formation then expands into a 6-aircraft presentation. White smoke traces turns, climbs, rolls, and formation changes across the sky, allowing spectators to follow the geometry of each maneuver. During the delta burst, the aircraft separate rapidly from the group and spread outward in different directions, creating one of the display's most recognizable moments. Repeated smoke trails make the formations visible from the ground as aircraft cross, climb, separate, and return again. Other sequences focus on single aircraft or pairs. F-16s make high-speed passes, fly low over the demonstration area, and perform individual aerobatic maneuvers before rejoining or clearing the display line. The program alternates between compact formations and separated aircraft, using different combinations to maintain continuous movement in front of the audience. The final stage returns the demonstration to the runway. The Thunderbirds descend, land, and taxi back after the aerial sequence is complete. Pilots then leave the aircraft and meet spectators, signing autographs and interacting with people at the event. Seen as one continuous operation, the show connects ground movement, formation takeoff, coordinated aerobatics, separation maneuvers, individual passes, landing, and post-flight activity. The F-16s provide the performance, but the video presents that performance as a carefully ordered sequence from the first taxi movement to the final return to the ground. Even perfect aircraft remain vulnerable to small objects left on the runway. The FOD Boss Airfield Sweeper is designed to collect foreign object debris such as screws, nails, stones, and metal fragments before they can damage tires or engines. Different configurations cover different widths. The triplex reaches about 7 meters, while the duplex covers roughly 4.8 meters. Towed behind a vehicle, the system can sweep at speeds up to 40 kilometers per hour and is described as collecting more than 99% of debris. It uses no motors or vacuum system, requires no routine maintenance, and can operate on wet, hard surfaces. When work is finished, the sweeper can be detached, rolled up, and packed for transport, making runway protection simple and mobile between sites. Runway protection preserves active aircraft. Museums preserve the machines that came before them. A World War II torpedo bomber is moved from the Quonset Air Museum in Rhode Island. The aircraft is dismantled into sections, loaded onto oversized transport trucks, and carried by road toward its museum destination for preservation. Preserving aircraft history contrasts with a component replaced repeatedly in daily service: tires. Commercial aircraft tires combine synthetic rubber, steel, nylon, and aramid fabric, and are inflated with nitrogen. Special grooves clear runway water. A tire may endure about 500 landings, can be retreaded up to 7 times, then may be recycled for other uses. After assembly, aircraft must prove their moving systems before returning to flight. In a hangar, a Boeing 747-400 undergoes a landing gear retraction and extension check. The gear doors open first, allowing the main and body gear assemblies to fold upward into their bays. Once every wheel is stowed, the doors close. The sequence then reverses. Doors reopen, the gear assemblies descend, rotate into position, and lock down for landing. Technicians watch the movement in final down and locked condition, confirming that the aircraft can transition safely between flight configuration and landing configuration. The same test becomes more imposing when the aircraft is the Airbus A380. With the airframe supported in the hangar, technicians cycle a landing gear system built around several multi-wheel assemblies. Gear doors open to expose the mechanisms beneath the wings and fuselage. The gear units, including 4-wheel and 6-wheel assemblies, retract in sequence. Each structure must rotate, fold, and move through a confined path before fitting inside its bay. Doors then close over the stored wheels, restoring the external shape required for flight. For the extension check, the process runs in reverse. Doors open again, the assemblies descend, straighten, and reach their landing positions. The test continues until the gear is fixed safely in the extended state. The test makes the A380's landing gear complexity visible. Multiple wheel assemblies and gear doors must move through the retraction sequence, then return outside and remain fixed in the safe landing position once again. Testing becomes even more revealing when engineers isolate individual landing gear assemblies. On another Boeing 747 in a maintenance hangar, technicians perform retraction and extension checks while the aircraft is raised clear of the floor on jacks. Instead of cycling all 4 major gear assemblies together, the crew tests one set at a time, or sometimes 2 simultaneously. The reason is the available ground power. According to the video notes, the ground pneumatic source cannot supply enough capacity for every air-driven hydraulic pump, or ADP, to operate at once. Dividing the test reduces the demand while still allowing technicians to observe each mechanism through a complete movement cycle. The body landing gear and wing landing gear on the left side are examined in detail. Gear doors open, the wheel assembly moves downward, and the structure reaches its locked landing position. The sequence is then reversed as the gear folds, rotates, and retracts back into the aircraft. Views from beneath the fuselage show why the mechanism requires careful inspection. Multiple wheels, hinges, braces, doors, and actuators must move around one another without interference. Wider angles from the rear and side reveal the relationship between separate gear units while the aircraft remains supported above the floor. This staged approach turns a complicated system into a series of observable actions. Technicians can watch door timing, hydraulic response, folding geometry, and locking behavior, without demanding maximum output from the ground pneumatic equipment. The test is therefore more than a dramatic display of wheels disappearing into the fuselage. It is a controlled method for confirming that individual components and complete assemblies travel through their required paths correctly. Before the 747 can depend on these systems during an actual landing, each mechanism must demonstrate that it can extend, lock, retract, and repeat the sequence under maintenance conditions without hesitation.